Welcome back to KSET previous year question and solution classes. Today I will discuss condensed matter physics questions, solid state physics and material science part. Okay. So here the question is like this. So this is 2016 paper. The question is based on density of states. Density of states in the conduction band for electron assumed to be essentially free in two dimension is proportional to. See, if suppose this is density of states and this density of states is proportional to e power minus 1 by 2 for 1D box for a one dimension, and density of states is directly proportional to e power 0. That means it is independent to energy only for two dimension, and density of states is proportional to e power 1 by 2 for 3 dimension. So therefore answer is density of states is proportional to for a two dimension is e power 0. So this is the special case. So for a two dimension density of states is independent of E naught. So that's why it has more wide applications in modern days, especially in dealing with nanoparticles. And in the second question, in the long wavelength region, the dispersion relation for manganese in a ferromagnetic in one dimension with the nearest neighbor interaction yields. So for that omega is equal to k square. This is a correct option. Next, in an allowed band of semiconductor, the effective mass m of the electron is infinite. The effective mass m is infinite. We know that the effective mass m for a semiconductor is m star is equal to h cross divided by d square E by dk square. Okay. And if we take d square E by dk square is equal to 0, then m star is equal to h cross divided by 0. So what it means? It means h cross by 0 is infinity. So that's why d square by dk square means what? It is equal to 0. 0 is always in the middle between negative and positive. Okay. So that's why answer is in the middle of the energy band, effective mass is infinite. Okay. So this is question number 55. The polarization P in a solid dielectric is related to the electric field E and electric flux density D by the relation polarization. So what is polarization? If a dielectric material is placed in an external uniform electrostatic field, a dipole moment is induced, a net dipole moment is induced in the dielectric material, and this process is called polarization. So, and if suppose let us take this is a dielectric material, if dielectric material is placed in an external electrostatic field, a polarization P is created, and this polarization is directly proportional to number of charges. So there are two types of charges in this dielectric material. One is bound charges, another one is free charges. So therefore the net density of the charge is rho f plus rho b. This is free charge and this is bound charge. We know that del dot E is equal to rho by epsilon naught, which is equal to rho f plus rho b divided by epsilon naught. Okay. So, therefore, del dot, this send epsilon naught to this side. So, del dot epsilon naught E is equal to del dot epsilon naught E is equal to rho f plus rho b, and rho b is nothing but minus del dot p. Therefore, del dot epsilon naught E is equal to rho f minus del dot p. Okay. Therefore, we can write that as del dot epsilon naught E. If I send that minus del p left side, it will becomes plus del dot p is equal to rho f, and therefore, which is equal to del dot epsilon naught E plus p is equal to rho f, and this epsilon naught E plus p is nothing but d. D is equal to epsilon naught E plus p. So, this is a field in dielectric material. So, that is epsilon naught E plus p. Where is there epsilon naught E plus p? So, option number C, epsilon naught E plus p, D is equal to, this is a correct option, answer C. Okay, understood? Next, question number 56, paramagnetic susceptibility of Fermi gas of conduction electron is proportional to 1 by T, proportional to 1 by T cube, proportional to 1 by T square, and independent of T. So, paramagnetic susceptibility for a Fermi gas is independent of temperature. And next question, heat capacity of a superconducting state is proportional to e power minus delta divided by kBT, where delta is energy gap. So, option D is correct. So, this is the question number 59 based on medelung constant. So, the chapter is from the chapter of atomic bonding. The medelung constant for the one dimensional crystal infinite line of ions of alternating signs plus minus is. So, medelung constant alpha can be calculated for infinite number of ions will be there, and these ions are like plus minus. So, let us take that is like this, plus minus so on. Okay. So, let us take any one of the ion for the reference. I am going to take, this is my reference, and from this reference ion, so this positive ion, they are separated by a distance r0, and this ion is separated by a distance 2r0, and this ion is separated by a distance 3r0. Okay, this is 3r0 and this is 2r0 and this is r0. We know that the potential energy U is equal to charge into potential. So, therefore, potential energy, total potential energy U is equal to Q. For these two charge, I am going to take minus Q plus Q is minus E square divided by 4 pi epsilon naught into the distance is 1 by r naught. And here I am going to write this 2 because for this ion one more positive charge is there here. So, there are 2 ions. So, that is why I am going to take 2. Next, minus. Next, for these 2 charges, minus into minus plus. So, plus 2. Why 2? Because one more charge is here. So, 2 E square divided by 4 pi epsilon naught into 1 by the distance between these two charges 2 r naught. And for third one, minus 2 e square divided by 4 pi epsilon naught into 1 by 3 r naught. And next for 2 e square divided by 4 pi epsilon naught into 1 by 4 r naught for this charge. So therefore, which is equal to, if I take 2 e square by 4 pi epsilon naught and 1 by r naught as a constant, so then it is if I take minus also as a common, so then it is 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus so on. Okay. So we know that ln 1 plus x is equal to x minus x square by 2 factorial plus x cube by 3 factorial and so on. If it is 1, so then ln 2 is equal to 1 minus 1 by 2 factorial plus 1 by 3, sorry, not 3 factorial, it is just 3 minus and so on. So therefore, it is just like that only, 1 minus 1 by 2 plus 1 by 3 and so on. So therefore, I am going to write this as this constant. Let us take this constant into, which is equal to and this minus is also included in the constant. So into and 2 right here. So that constant into 2, and this is just like ln 2. So this is our alpha medelung constant. So therefore, energy U is equal to minus E square divided by 4 pi epsilon naught into 1 by r naught into alpha. That alpha is medelung constant and that alpha is 2 ln 2. So that alpha is 2 ln 2. Okay. So option number D is correct. So this is the question number 60. The low temperature heat capacity of insulators will be proportional to. So we know that heat capacity CV is equal to A T plus B T cube, and A T is contribution of electrons and B T cube is contributions of phonon. But in an insulator, the contribution of electrons is 0. So therefore, CV is proportional to T cube. So option C is correct. Okay. Next, and at any temperature the probability of occupation of electron at Fermi energy. Fermi energy means highest energy. In the energy level, the highest energy level is called the last filling energy level is called Fermi level, and we know that f of E is equal to 1 divided by e power E minus mu divided by kBT plus 1. And at all temperature, if E is equal to EF and which is equal to mu, then E minus mu is equal to 0. So therefore, when E minus mu is equal to 0, then f of E 1 divided by e power 0 plus 1, which is equal to 1 by 1 plus 1, which is equal to 1 by 2. At all temperature, when E is equal to EF and that is equal to mu, then the Fermi energy is 1 by 2. And next, the Wigner-Seitz cell for any two-dimensional bravais lattice. For any two-dimensional bravais lattice, and Wigner cell contains at least one lattice point in a unit cell. So, therefore, it has to be hexagonal or rectangular. So, therefore, option number C is correct. So, this is the question number 63. The Lane condition for X-ray diffraction is G is the reciprocal lattice vector. Okay. So, we know that if suppose this is a lattice point, and for this lattice point, suppose let us consider a ray is incident and some of the rays get reflected, okay, some and scattered. So, I am going to write this diagram like this. If suppose this k is vector k is scattered vector, outgoing vector, and vector k prime is a incoming vector, and delta k, and this delta k is equal to G is the reciprocal vector or scattering vector. Okay. So, therefore, now from this triangle, from the right angle triangle rule or some vector rule, a triangle of vector addition, k prime is equal to k vector is equal to k prime plus delta k, okay, or k vector is equal to k prime plus G. Now, from the parallelogram of vector addition, we know that modulus of k is equal to square root of modulus of k square plus G square plus 2 kg, and if there is no square means this is also square. Since k vector is equal to k prime, or the magnitude of k is equal to magnitude of k prime. So, therefore, these two vectors will get cancelled, and the remaining is G square plus 2 kg is equal to 0, or 2 kg is equal to minus G square. So, is there any option like that? 2 k dot G. So, in terms of vector notation, we can write 2 k dot G is equal to minus of G square. If it is minus, it is the correct option. Okay, here minus sign is missed, I think. So, option number A is correct. And here assert A, van der Waals type bonding single crystal do not exist at room temperature. Correct. And reason R, van der Waals type single crystal are lightweight. No. So, option C, A is correct and R is wrong. So, option C is correct answer, because van der Waals type bonding single crystals does not exist at room temperature. Okay. So, this is question number 66. KCl crystal has a density of rho. So, the density rho is equal to 1.98 into 10 to the power of 3 kg per meter cube, and its molecular weight. So, molecular weight M is equal to 74.55 grams, and the interatomic distance N. So, the interatomic distance we are going to calculate. So, A you have to calculate, and N Avogadro number is given. N is equal to 6.023 into 10 to the power of 23 gram per atom. So, So, next, therefore, we know that A cube is equal to N effective and mass atomic weight divided by density into Avogadro number N. Okay. So, therefore, A is equal to N effective and mass number atomic weight into rho N whole power 1 by 3. If you substitute their corresponding constants and calculate, we will get A is equal to see, I will substitute that. A is equal to N effective is 4, okay, because of FCC it is 4 number of lattice points or atoms per unit cell. So, 4 into 74.55 divided by rho 1.98 into 10 to the power of 3 into 6.023 into 10 to the power of 6. So, whole power 1 by 3, we will get 6.3 into 10 to the power of minus 10 meter. So, option C is correct. And here match the following and identify the correct meaning in the choice below. So, here the direct lattice and reciprocal lattice are given. For simple cubic is reciprocal lattice, and for BCC, FCC is reciprocal lattice, and for FCC, BCC reciprocal lattice. So, therefore, A to P and B to A to R and B to P and C to Q is the correct option. The reciprocal lattice for FCC is BCC and for BCC is FCC and for simple cubic itself.